In the last video, we said that kinematics helps us understand the geometry of motion. Specifically, it helps us determine an object's position, velocity, and acceleration. Recall that these are all three vector quantities and therefore have both magnitude and direction. For position, we use the variable r. Note that the book often uses a scalar quantity called s, but then switches to the vector r later in chapter 12, so I will just start with r. We always express position of an object with respect to another point. So the position of the particle p with respect to point E, as shown at the right, could be written as xex plus yey plus zez. Now let's assume that the particle is traveling along the path indicated by s of t. It has a velocity that is always tangent to the path of motion. So in this case, we could write the velocity of p with respect to e is vxex plus vyey plus vzez. And you might correctly point out that the vertical component of the velocity, vy, will be negative in this case. The magnitude of any velocity is speed. It is usually given by the variable v without an arrow over it, since it is a scalar. This is computed as the sum of the squares of the components of velocity in each direction. As with velocity, we can express an object's acceleration vector in terms of the unit vectors of a convenient reference frame. Here, acceleration could be written as axex plus ayey plus azez. The magnitude of the acceleration is computed as the square root of ax squared plus ay squared plus az squared. Position, velocity, and acceleration are related, and there are three basic kinematic equations that can help us understand how. I'm going to do a quick derivation of these equations. Although I want you to see it once, I will never ask you for a derivation on a quiz or exam. So to start, consider a particle p moving along a path s of t. Suppose that over some time interval, the particle moves from s naught at time t naught to s1 at time t1. Its distance traveled is given by delta s equals s1 minus s naught. Now let the r sub p slash e be a vector that describes the position of p with respect to point E. Point E is fixed in inertial reference frame E, and in fact, it's the origin of reference frame E. Position vector r is a function of time, such that in Cartesian coordinates, it is x of tex plus y of tey plus z of tez. Let delta r be the change in position or displacement of the particle over time, such that delta r equals delta xex plus delta yey plus delta zez, and delta x, delta y, and delta z are as shown. Distance traveled, delta s, is not the same as displacement, delta r. However, for small time intervals, their magnitudes are approximately equal. So the limit of delta r as delta t approaches 0 is delta s. Then, if the velocity is the limit of delta r over delta t as delta t approaches 0, the velocity is dr dt. Similarly, if acceleration is the limit of delta v over delta t as delta t approaches 0, then acceleration is dv dt, which is the same as the second derivative of the position vector with respect to time. In fact, these are the two main kinematic equations for one-dimensional, two-dimensional, and three-dimensional translational motion. If we solve equations 1 and 2 for dt, we obtain a third equation, but please note that only two equations are independent. That is, you can't solve for three unknowns using these three equations. You can only solve for two unknowns. In any case, this is all of kinematics right here in these three equations. Unfortunately, applying these equations in various situations takes some practice, and so we will spend several weeks practicing this. But this is really all there is to kinematics. So if you haven't downloaded the course formula sheet yet, please do that soon. You'll find that these three equations are the first three equations on it. So remember that position, velocity, and acceleration are vectors that vary over time, and when we work problems, we need to add the endpoints of the vectors. So the equations will typically look like this with subscripts, where p is the particle of interest and e is the inertial reference frame. You might notice that the book frequently omits the base point or the inertial reference frame e from the subscript. This is okay, but we'll soon start working with more than one reference frame, and it will be helpful if we keep track of each base point and reference frame. Also note that the velocity vector is always tangent to the path of motion. We'll talk more about this later, so you don't really need to remember it just yet. We're going to be working with particles for the first few weeks of the course. Particles are idealized objects that don't exist in the real world, but it can be useful and reasonable to model objects as particles in some instances. Particles have mass, but negligible size and shape. Particles are subject to translation, but not rotation. There are two types of translational motion. Rectilinear means that the path of motion is in a straight line, it's one-dimensional. Curvilinear means that the path of motion is curved, it's two or three-dimensional. In terms of analysis, we will start with rectilinear motion. So we'll now start using the kinematic equations in situations where there's rectilinear continuous motion of a particle. Rectilinear means that the path of motion is in a straight line, like we just said, it's one-dimensional. Continuous means that the position of the object can be described with only one equation. So let's practice this with an example. Here we're told that a particle p is moving along a straight line with speed t squared plus 2t, and that's in meters per second, noting that t must be in seconds. If the particle's position is 0 meters when t is 0 seconds, we need to find its acceleration and position when t is 3 seconds. To solve this problem, start by drawing a picture and adding an Earth-fixed reference frame. In this case, an origin and a single unit vector will suffice, but I'm going to go ahead and draw the three axes for completeness. Next, add the particle and its position vector with respect to the origin of the reference frame. For problems like this, it's helpful to identify the information that we have and the information that we need. In this case, we know the magnitude of the velocity and time, and we need the acceleration and position vectors. We can't solve for acceleration and position simultaneously, so we'll have to start with one. In this case, let's arbitrarily choose to start with position. Since we have velocity and time, and now we need position, equation 1 would be the best fit here. I'm going to rewrite equation 1 with the appropriate subscripts for this problem. Here we're interested in the position and velocity of p with respect to e. Next, we rearrange this equation to separate the differential terms. Now we need to substitute an expression for velocity. We were given the magnitude of the velocity in the problem statement, but velocity is a vector. To convert the scalar quantity to a vector quantity, just add the unit vector that's appropriate based on your picture. Remember, vectors always have magnitude and direction and usually units. Since velocity is always directed along the path of motion, it must be in the EX direction in this case. So now we can substitute. And note that the velocity is a function of time t, and t is given in seconds. But also note that the units of time do not contribute to the units of velocity, which is in meters per second. In this case, t is just a parameter. This happens a lot in dynamics, and it can be confusing, so I wanted to point it out. It's important to keep track of units, but in this case, we can ignore the units of seconds associated with time for the purposes of computing velocity. So moving on, we can integrate. One thing that you may or may not remember from calculus is that the limits of integration must always match the differential term. So in this case, on the left, we have dr, and the limits of integration are position values. On the right, we have dt, and the limits of integration are time values. Note also that the upper limits of integration are just r and t. We didn't plug in any values. This is the best way to work these problems since it will give us a final expression that works for any point in time after the initial conditions. In general, you should avoid plugging in values for the final time until the very end of the problem solving process. So continuing, we integrate. Note that the units for velocity were meters per second, but since we integrated over time, we need to multiply by seconds. Hence, we have units of meters now. Next, we can plug in the time of 3 seconds, and we find that the position of particle p with respect to e is 18 meters in the ex direction. Note once again that this vector has magnitude, direction as indicated by the unit vector ex, and units. So last, we need to find the acceleration vector when t is 3 seconds. Identify the information we have. So this is velocity, and we have it in the form of a vector now, and time. We need acceleration. So choose the equation that contains those variables, and that's going to be equation 2. Write it with the appropriate subscripts. Then substitute the expression for velocity. This is the same as before, and take the derivative. Remember in the last step we were integrating and we had to multiply the units by time? In this case, we are taking the derivative, so we need to divide the units by time. Then plug in the value of t, which is 3 seconds, and we find that acceleration of p with respect to e is 8 meters per second squared in the ex direction.